Now, just hold your horses, everyone. Let's let it run for a minute or so and see if it gets any colder. That's the Far Side cartoon for the day. And today's goal is to describe the special properties of water that contribute to Earth's suitability as an environment for life. And the listed here are cohesive behavior, ability to moderate temperature, expansion upon freezing, and versatility as a solvent. Let's look at our goals, our objectives, Discuss the unique properties of water, differentiate between solutions and suspensions, and explain what acidic solutions and basic solutions are. So think about it. Looking back at Earth from space, an astronaut called it the blue planet, referring to the oceans of water that cover nearly three-fourths of the Earth's surface. The very presence of water tells a scientist that life may also be present on such a planet. So why should life itself be so connected so strongly to something so ordinary that we often take it for granted? There is something very special about water and the role it plays in living things. Water is the biological medium of on Earth. All living organisms require water more than any other substance. Human beings can survive for a few weeks without food, but only a few days without water. In fact, most cells are surrounded by water, and cells themselves are about 70 to 95% water. Water is the only common substance to exist in a natural environment in all three physical states of matter, as you know, solid, liquid, and gas. And finally, the abundance of water is the main reason the Earth is habitable. So let's look at objective 1. Discuss the unique properties of water. And there are quite a few, and they're quite in-depth, so bear with me, please, and please pay close attention. The first one has to do with polarity, all right? Actually, most of them have to do with polarity and hydrogen bonding. Let's talk about the polarity and review that a little bit first. As you remember, oxygen has 8 protons, okay? So water's oxygen nucleus attracts electrons more strongly than the single protons of the 2 hydrogen nuclei. So most of the electrons are hanging around the oxygen molecule, the oxygen element there. As a result, water's shared electrons are more likely to spend more time around the nucleus of the oxygen atom. Because of the angles of its chemical bond, the V shape, the oxygen atom is on one end of the molecule, and the hydrogen atoms are on the other. This gives water a partial negative charge on this end and a partial positive charge on this end, making it polar, because the molecule is a little bit like a magnet with 2 poles, a negative and a positive side. All right. Another thing is hydrogen bonding. The slightly positive hydrogen of one molecule of water is attracted to the slightly negative oxygen of a nearby molecule of water. So you have many, many molecules of water, obviously, when you're talking about a cup of water, right? So they're all attracted to each other because of the hydrogen bond. The 2 molecules are thus held together by a hydrogen bond, as you can see from the picture here. The negative oxygen and the positive hydrogen, they're attracted to each other from that. So when water is in its liquid form, its hydrogen bonds are fragile, each about 1/20th as strong as the covalent bond between the hydrogens and the oxygen itself. So hydrogen bonds can form, break, and reform with frequency. Each bond, as a matter of fact, only lasts a few trillionths of a second, but the molecules are constantly forming new hydrogen bonds with the successions of partners, like they're bouncing around and they're bonding back and forth together. So because water is a polar molecule, it is able to form multiple hydrogen bonds, which account for many of the water's special properties. Let's look at the first one we're going to discuss. So keep in mind polarity and hydrogen bonds when we talk about these properties of water. Cohesion. Cohesion is an attraction between molecules of the same substance. Because a single water molecule may be involved in as many as 4 hydrogen bonds at the same time, water is extremely cohesive. Cohesion causes water molecules to be drawn together, which is why drops of water form beads on a smooth surface, like a car when it's been waxed. Cohesion also produces surface tension too, explaining why some insects and spiders can walk on a pond surface. These linkages make water more structured than most other bonds. Cohesion due to hydrogen bonding contributes to the transport of water and dissolved nutrients against gravity in plants. Water from the roots reaches the leaves through a network of water-conducting cells, and as water evaporates from the leaf, Hydrogen bonds cause water molecules leaving the veins to tug on molecules further down, and the upward pull is transmitted through the water-conducting cells all the way down to the roots. Another thing that water has is adhesion. Adhesion is an attraction between molecules of different substances. So remember, cohesion is similar molecules, adhesion is different substances. So the surface of water in a graduated cylinder, if you've ever seen this, will dip slightly in the center like this, forming a curve called a meniscus. Because the adhesion between the water molecules and the glass molecules right here is stronger than the cohesion between the water molecules. Adhesion between water and glass also causes water to rise in narrow tubes against the force of gravity. This effect is called capillary action. Capillary action is one of the forces, like cohesion, that draws water out of the roots of a plant and up into the stems and leaves too. So far we have cohesion and adhesions. That's a property of water. The next thing we're going to talk about is the heat capacity. Let's review what heat is first though. Anything that moves has kinetic energy, which is the energy of motion. Atoms and molecules have kinetic energy because they are always moving. The faster a molecule moves, the greater its kinetic energy. Heat is a form of energy, and although heat is related to temperature, they are not the same thing. We use the Celsius scale to indicate temperature. And for your information, in Celsius, 0 degrees is what water freezes at, and 100 degrees is what water boils at. The temperature of the average body temperature is 37 degrees Celsius, and a comfortable room temperature is about 20 to 25 degrees Celsius. So a convenient unit of heat, 1 unit of heat is a calorie. And how do we measure calories? A calorie is the amount of heat it takes to raise the temperature of 1 gram of water by 1 degree Celsius. Conversely, a calorie is also the amount of heat that 1 gram of water releases when it is cooled by 1 degree Celsius too. So heat capacity is what we're talking about for water here. Compared to most other substances, water has a very high heat capacity. Heat capacity can be thought of as a measure of how well a substance resists changing its temperature when it absorbs or releases heat, meaning it takes a lot of heat energy to increase the temperature of water. For example, when we talk about ethyl alcohol, it has a specific heat capacity of 0.6 calories per gram. That is, only 0.6 calories is required to raise the temperature of 1 gram of alcohol by 1 degree Celsius. The reason you can burn your fingers by touching the side of an iron pot on the stove when the water in the pot is still only lukewarm is that the heat capacity of water is 10 times greater than that of iron. The water hasn't gotten heated up yet, even though the iron is already hot from the stove, the pot I mean. Water resists changing its temperature. When it does change its temperature, it absorbs or loses a relatively large quantity of heat for each degree of change. So water's high heat capacity, like many of its other properties, is due to the hydrogen bonding. Heat must be absorbed in order to break hydrogen bonds and released when the hydrogen bonds are formed. So how is this relevant to life on Earth? Ugh. All right. A large body of water can absorb and store a huge amount of heat from the sun in the daytime and during the summertime, while only warming up only a few degrees. And at nighttime and during the winter, another example, the gradual cooling of the water can also warm the air. Think about what kind of implications this means for Florida, a state that's surrounded by water. The high heat capacity of water also tends to stabilize the ocean temperature, creating a favorable environment for marine life. Because of the high heat capacity, the water that covers most of the earth keeps temperatures fluctuations on land and in water within limits that permit life to exist. Also, because organisms are made primarily of water, they are better able to resist the changes in their own temperature too. Another interesting fact about water is called evaporative cooling. Molecules of any liquid stay close together because they are attracted to one another. Molecules moving fast enough to overcome these attractions can depart or leave the liquid stage and enter the air as gas. This transformation from a liquid to gas is called vaporization or you probably know it as evaporation. Water's high heat of vaporization or evaporation is another emergent property resulting from the strength of its hydrogen bonds. As liquid evaporates, the surface of the liquid that remains behind cools down. This evaporation cooling occurs because the hottest of the molecules are the most likely to leave as gas, leaving behind the cooler molecules. It's kind of an example, it's like it is as if the 100 fastest runners at school were to leave school, be transferred to another school, then the average speed of the remaining students would decline. Evaporative cooling of water contributes to the stability of temperature in lakes and ponds and also provides mechanisms that prevent land organisms from overheating. For example, water evaporating from the leaves of plants helps keep the tissues in the leaves from becoming too warm in the sunlight. And evaporation of sweat from the human skin dissipates body heat and helps prevent overheating on a hot day or during strenuous exercise. High humidity, on the other hand, on a hot day, increases the discomfort because of the high concentration of water vapors in the air inhibits the evaporation of sweat from the body. So like we have in Florida, hot, humid days, you're out playing tennis, you're still going to feel hot and humid. It's not very comfortable. If you go to New Mexico and you jump in the pool to cool off, when you get out, you're going to be really, really cold because the water is being evaporated off of you so quickly. It's really an interesting phenomenon. But sweating is very important to help keep us cool. Another concept with water is floating of ice on liquid water. Water, in fact, is one of the few substances that are less dense as a solid than as a liquid. In other words, ice floats on water. You've seen it everywhere in a cup of ice, a glass of water with ice. Once again, this is due to the hydrogen bonding. As temperature goes down from 4 degrees Celsius to 0, water molecules begin to move too slowly to break the hydrogen bonds. At 0 degrees, the molecules become locked into a crystalline lattice, each water molecule hydrogen bonded to 4 partners. The hydrogen bonds keep the molecules at a slight distance apart from each other, far enough to make ice about 10% less dense than liquid water at 4 degrees Celsius. By the way, water is most dense at 4 degrees Celsius and then begins to expand as the molecules begin to move faster. The ability of ice to float due to its lower density is an important factor for life. Why is that? If ice sank, then eventually all the ponds, lakes, and even the oceans would freeze solid, making life as we know it impossible on Earth. Instead, when a deep body of water cools, the floating ice insulates the liquid water below, preventing it from freezing and allowing life to exist under the frozen surface. Here is water frozen, what the molecules would look like, and here is water as liquid. You can see the molecules are bouncing around at each other and closer together. So water is less dense when it's frozen. So let's review Objective 1, discuss the unique properties of water. Because water is a polar molecule, it is able to form multiple hydrogen bonds, which account for the multiple unique properties of water, like cohesive and adhesive behavior, the ability to moderate high temperature, which is high heat capacity, and expansion upon freezing, and what we're going to discuss next, versatility as a solvent. So Objective 2 is differentiate between solutions and suspensions. Let's look at some vocabulary first. A solution is a liquid that is a homogeneous mixture of substances. A solvent is the dissolving agent of a solution. A solute is the substance that is dissolved. And an aqueous solution is one in which water is the solvent. Little history here. During medieval times, chemists tried to find a universal solvent, one that would dissolve anything. And guess what they learned? They learned that nothing works better than water. Yet, water is not a universal solvent. A universal solvent would be able to dissolve anything. If water were a universal solvent, then it would dissolve any container in which it was stored, including our cells too. But water is a very versatile solvent, a quality that can be traced to the polarity of the water molecule. Many different kinds of polar compounds are dissolved in water, such as biological fluids like blood, the sap of plants, and the liquid within all cells. Water is the solvent of life. Water is not always pure, is often found in a mixture. A mixture is a material composed of two or more elements or compounds that are physically mixed together but not chemically combined. Living things are in part composed of mixtures involving water. There are two types of mixtures that can be made with water. They are called solutions and suspensions. Look at solutions first. Water easily dissolves salts, sugars, minerals, gases, and either other solvents such as alcohol. When a given amount of water has dissolved all of the solute it can, the solution is said to be saturated, meaning if you add any more of the given solute, it will not dissolve. Two types of mixtures that can be made with water are solutions and suspensions. I already said that, didn't I? If a crystal of table salt is placed in water, sodium chloride ions on the surface of the crystal are attracted to the polar water molecules. Ions break away from the crystal and are surrounded by the water molecules. The sphere of water molecules around each dissolved ion is called a hydration shell. The ions gradually become dispersed in the water, forming a type of mixture called a solution. The resulting solution is made up of two solutes, sodium cations and chloride ions. Anions, homogeneously mixed with the water, the solvent. Some materials do not dissolve when placed in water, but separate into, here's some vocabulary, but separate into pieces so small that they do not settle out. Such mixtures of water and non-dissolved material are known as suspensions. Some of the most important biological fluids are both solutions and suspensions. Blood is mostly water. It contains many dissolved compounds, but it also cells and other undissolved particles that remain in suspension as the blood moves through the body. So cells are in the blood, right? So they may remain in suspension. There are two different types of substances when it comes to talking about water. There is hydrophilic, which is a substance that has an affinity for water, which means it's attracted to the water. And there's hydrophobic, which is a substance that does not have an affinity for water, which means it repels against it. Oil molecules are hydrophobic because they have relatively non-polar bonds. You understand that? Oil molecules are hydrophobic because they are non-polar bonds. They don't have the positive and negatives. So the water molecule has nothing to bond onto like a magnet would, positive and negative does. So you have to have that positive and negative for the water molecule to break it apart. Although that makes it hydrophilic. It's hydrophobic if the molecule has no polarity. Some molecules that are hydrophilic are also so large that they do not dissolve. Instead, they remain suspended in the aqueous liquid. So objective 2 was to differentiate between solutions and suspensions. So mixtures of water and non-dissolved material are known as suspensions. A solution is a liquid that is a homogeneous mixture of substances. And we'll review this in class 2. Objective 3. Explain what acidic solutions and basic solutions are. All right, so sometimes a hydrogen atom participating in a hydrogen bond between two water molecules shifts from one molecule to the other. When this happens, the hydrogen atom leaves its electron behind. What is actually transferred is a hydrogen ion, which we denote as H+. It's a single proton with a charge of 1 positive. The water molecule that lost a proton is now a hydroxide ion, which has a charge of a negative. Now, the water molecules that have split apart form hydrogen ions and hydroxide ions. This reaction can be summarized by a chemical equation in which double arrows are used to show that reaction can occur in either direction. Let me show another picture that might help make it more clear here too. All right. Although the dissociation of water is reversible, it is exceedingly important in the chemistry of life. Hydrogen ions, H+, and hydroxide ions are very reactive. Changes in their concentration can drastically affect a cell's proteins and other complex molecules. The concentration of H plus and OH are equal in pure water, but adding certain kinds of solutes called acids and bases can disrupt this balance. Biologists sometimes use something called the pH scale to describe how acidic or basic a solution is. An acid is any substance that increases the H plus concentration of a solution, and a base is any substance that reduces the H plus concentration of a solution. And by the way, pH stands for potential hydrogen. Chemists devised a system called the pH scale to indicate the concentration of H plus ions in a solution. The pH scale ranges from 0 to 14. At a pH of 7, the concentrations, right about here, of H plus ions and OH negative ions is equal. Pure water has a pH of 7. Solutions with a pH below 7 are called acidic because they have more H plus ions than OH negative ions. The lower the pH, the greater the acidity. Solutions with a pH above 7 are called basic because they have more OH negative ions than H plus ions. The higher the pH, the more basic the solution. Most biological fluids have pH values in the range of 6 to 8. Normal blood pH is between 7.35 and 7.45. A lower or higher pH can be a sign of ill health. Each step on the pH scale represents a factor of 10. So a liter of a solution with a pH of 4 has 10 times as many H plus ions as a liter of a solution with a pH of 5. So you just increase by one step, but it's 10 times as many. Keep that in mind. That could be on the test. What are buffers? Buffers, as you remember, the pH of human blood is very close to 7.4, which is slightly basic. A person cannot survive for more than a few minutes if the blood pH drops to 7 or rises to 7.8. And a chemical system exists in the blood that maintains a stable pH for us. In fact, if you add 1/100th of a drop of strong acid to a liter of pure water, the pH will drop from 7 to 2.0. The same amount of acid is added to a liter of blood, however, the pH decreases only from 7.4 to 7.3. Why does this happen? Because of buffers. Buffers allow for a relatively constant pH in biological fluids, despite the additions of acids and bases. Buffers are substances that minimize changes in the concentrations of H plus and OH negatives in a solution. They do so by accepting the hydrogen ions from the solution when they are in excess and donating hydrogen ions to the solution when they have been depleted. That's the job of buffers, basically. They accept the hydrogen ions, they take care of them for us, or they give them back when needed to. There are several buffers that contribute to the pH solubility in human blood and many other biological solutions. So objective 3 was to explain what acidic solutions and basic solutions are. An acid is any substance that increases the H plus or hydrogen ion concentration of solution, and a base is any substance that reduces the hydrogen ions or H plus concentration of a solution. And finally, we will be reviewing this in class, as you know, but let's look over them. Maybe you get some good ideas here. And what we're talking about is to discuss the unique properties of water, differentiate between solutions and suspensions, and explain what acidic solutions and basic solutions are. Hope I gave you a good preview. Hope you took good notes and that you're ready for class tomorrow, because this chemistry stuff, wow, it's really interesting. And it is the basis for all biology. So we got to get it down and understand it. So have a good evening, guys. Adios.